Is ready. I'm very happy to introduce the next speaker, which is Ritchie. Welcome. And he's going to tell us all about going beyond Polars 1.0. I'm super curious. Take it away, Ritchie. Give him a big hand of applause.
Thank you. Wow, it's a big crowd. Let me start. Who already uses Polars? Can I get a show of hands? Nice, it's getting better and better. Last year it was 20%, so I think we are reaching 40. Who has heard of Polars? Okay, yes. I always need to start with some introduction what Polars is, and I hope that in the future years I can leave those out. So let's make that happen. Short introduction about me. My name is Ritchie Vink. I'm the original author of Polars. As of 1.5 years now, I'm also a co-founder and CEO of the like-named Polars company. And originally, I have a background in machine learning and software development. And today, I'm going to give a short introduction about Polars. And I'm going to talk about a new feature we just released this week. Is there some resonance, or is... which is GPU acceleration. This just released last Tuesday, so it's super fresh. And I'm going to talk about Polars 1.0, which we released in July, and what we're doing now. And I'm going to do a short demo. So originally, on a single node at least, people were thinking about data frames as some data structure which you could see as a list of series with some data in it. And when you did an operation, you would get back another data structure, right? That's how the mental model of data frames was when you work with pandas. Not per se when you work with PySpark, but when you work in R or in Python, this was the concept of a data frame. And with Polars, we like to think about data frames different. We like to think about data frames as an end result, but what's the most important part is the query engine part. So we see it as a query engine for data frames. So when you do an operation, you don't get a result immediately, but you build a DAG or a tree of operations. And every subsequent operation, you get an updated DAG or an updated tree. And when you force us to materialize a result, when you force us to materialize a data frame, an actual data frame, we will take that tree of operations and we will expect it and feed it to an optimizer. And this optimizer will shuffle it around and we'll see if he can prove that he doesn't have to do some code or doesn't have to read some columns or doesn't have to do a join operation or maybe can do it in a more efficient join, etc. This is very similar to what a compiler does. If you compile C to assembly, the compiler will never run your code as you've written it. It would always do something else. And once we've optimized it, we will feed it to the engine. The engine, there are multiple engines, but I'm going to abstract it as one engine for now. And as an end result, you will end up with a data frame, the actual data structure people think about when thinking about data frames. So I always have this slide in my talk. I think we always need it somewhat, but as a query engine, we respect decades of database research, because database research is actually where it's all about. When you operate on data, there are decades of research of how to do this efficiently, how to do this correctly, and you shouldn't ignore that, which is something we try to respect. So there's a list of stuff we do, and I can go through it, but then I would still miss a lot. So for now, I'm going to skip it, and you can take a picture. As a result, we are one of the fastest open source data frames on a single node. I think I'm not exaggerating here. When data fits in memory, Polars is one of the fastest open source solutions. Here you see Polars on a popular benchmark compared to DuckDB, to PySpark, to Pandas and Dask. Note this is Pandas with the PyArrow backend, just to get some rumors out of the air. Pandas on PyArrow is not faster than Polars, not by a long shot. Okay, now that's done. let's talk about the new feature we've got. GPU acceleration. Polars is already really fast, but for some people, you can make it even faster. And together with the NVIDIA Rapids team, we brought GPU acceleration to Polars. And to do that, we had some design considerations. One is, of course, the semantics must be the same. If you run Polars on the GPU, you should get the same result, right? You should get the same null data, etc. Same order of sort. That's obvious. Second, we need to use the optimizer. It doesn't make any sense to start accelerating data or accelerating work when you could have proven that you didn't need this work to do this work after all, right? What's the point of it? So that we had to use the optimizer. Another one is that there needs to be a hybrid execution model and a seamless fallback, because you don't want your query to just fail if this operation doesn't work on the GPU. Not every operation works on the GPU, so it should work hybridly. And we wanted this to be parts of the Polars library. So there should not be a Polars QDF second library, which you need to install and change one line of code, you know, that stuff. We wanted this to be embedded and actually, because this is embedded, we can make the first 3 points way easier. We can use the optimizer, we can use the same semantics, and the fallback. So from a user perspective, nothing changes. From a user perspective, well, almost nothing changes. You use Polars just as is, but if you want to collect a result, materialize a result, you can now pass an engine keyword, and you can pass the GPU keyword, and then the result will run on the GPU, and yeah, that's it. If it isn't able to run on the GPU, it will just run on the CPU, and we'll finish the query. But this feels a bit magic, so let's go through the roadmap of a query and see how this is achieved, how this is implemented. When you write a Polars query, the first thing we do, you, of course, write the query. You type in the query in Python. What we do on the back end is we build a DSL, a domain-specific language tree. You can think of this as the AST of Python, right? If you write Python, when you run Python, it builds a tree of the abstract syntax tokens you've written, or words, and there's semantics to that. There's semantics to what you've written, and that can be analyzed. So our comparative thing of that is a DSL. But with this DSL, we don't do anything yet until you call collect. Until you call collect, you force us to materialize. And at that point, we convert the DSL into an IR, an internal representation. And in this IR, we want to get the schemas of the data types. We want to see if the query is correct, maybe throw an error if you made a mistake, and get as much statically known information as possible. For us to be able to do that, we need to read the data at that point. So we go back to our data loader, which is async, which can already start prefetching data. This can be from S3, so you can already start downloading data, but we don't want to wait building the IR until all the data is downloaded, right? So we already prefetch some of the data, and with that, we can build the IR. Once the IR is built, we can feed it to the optimizer. It does the optimization passes. In the meantime, the downloading continues. And when the optimizer is done, you will get an optimized IR, and we will build a physical plan. This is all the logical phase. There's no execution yet, and that physical plan will be passed to an engine, and the engine picks up from the async data loader and gets all the data and tries to produce a result. This is the roadmap on a high level of a typical query. But there is, where do we now feed in the GPU engine? How we're going to make that work? So on the logical phase, we have the same tree. We go from DSL to IR, and then we go to the optimizer, which still runs on the CPU. And we get back this optimized IR, and then with this optimized IR, we feed this back to the QDF code. So we call back into Python, into QDF, and they can traverse this optimized IR and inspect, hey, can we do this join operation on the GPU? Can we read this packet on the GPU? They will inspect the IR and then see, okay, this part of the subtree is something we can replace and actually run on the GPU. So what they will do is they will replace that with a Python function, and this Python function has one promise: it will return a data frame. And when we call it, it will actually run on the GPU. So this is how it will look physical. In the Polars in-memory engine, we have a tree of operations that will be executed, and a part of this subtree can run on a GPU and produce this data frame. And then the CPU can take that result and continue on the CPU if needed. So that's how it works. And as a result, you can get even more speed-ups than on the CPU only. So these are the results on a comparable GPU. I mean, it's always different hardware, so it's hard to compare, but there's the same costs here. So it's a very performant CPU taken compared to a very performant GPU. And these are the results you can expect on the PyData, which is a benchmark derived from TPCH, and TPCH is a benchmark that's commonly used for database queries. It focuses on very fast join execution, but also it focuses on, does the optimizer recognize that it doesn't have to do this join, or can this do this join in a different order, or etc. And you can see that you can get speedups up to 13 times, varying speedups, and this is also to be expected, because Polars has a good optimizer, or it can always be better, but it has an optimizer that does a fairly good job and can prove that in sometimes it has to do minimal work and you're just I/O bound of the columns you need. On these queries, you would not see much of a performance increase on the GPU because you're not CPU bound, you're memory bound or I/O bound at that point. On query 21 or query 18, we are definitely CPU bound. This query turns out to have a lot of join operations, a lot of group bys, and if there feeds a lot of data through a join operation, you're doing a lot of work. It's just a lot of work to finish that join. And here you can see that a GPU really can make a difference. So you can read more on our GPU engine release. I have a demo as well, which I started to do do some downloads. And if I have time, I want to come back to this at the end of this presentation. I just want to run one thing to make sure that the notebook stays alive. It seems alive, good. And now I want to come back. So that's the part of Polars on the GPU. This is, yeah, I'm pretty excited about this release. We made this release last Tuesday, and we're going to go to the demo a little bit later to see how it works. How the whole engine works, we've abstracted that, right? I just said different engines. We use different techniques for this. We use work-stealing parallelism. I've explained more about this in other keynotes I gave, but I don't have the time to repeat that here, so I want to give you this slide with the talks to this. If you're interested how the engines actually work and what they're doing, yeah, take a look at these presentations. So, Polars 1.0, this is a big milestone for us. We're finally with the big boys now. It feels like that. So yeah, we reached 1.0 July 1st, 2024. And what this means for us is stabilization of our API. We've been experimenting a lot. Polars is not only developing a whole query engine, Polars is also developing its own DSL, its own domain-specific language. It's not the Pandas API, it's the Polars API. And we really have tried to experiment here and really try to understand what's a good API to do ergonomic data processing, but also keep parallelism possible and make sure that it's performant. And that the optimizer has insight in what you're trying to achieve. So that's sometimes those things are contrary, sometimes they're not, and that's stuff we've been experimenting with. We're still learning about this, and we're still improving here, but we're fairly confident that our API makes sense now, and that we can improve upon this, and we don't need that many breaking changes in the semantics of our API anymore. It's not that they won't happen, it's that we're much softer than before 1.0. And since 1.0, we have still been busy, we've still been doing a lot. So this is a bit of a cherry pick of different things we've been working on in the last 3 months. It's only been 3 months, but we've been working on a lot of stuff still. So we've been working on one huge thing, is very boring, is correctness. And I'm going to come back to this, why this takes a long time, but why it is useful for you, but it doesn't sound as sexy as, hey, we have this new shiny feature. Another thing is improved Parquet performance. We're building Polar's Cloud, which the goal is that you can scale Polars beyond a single machine. I think we're really good on a single machine, but we want to make this same API possible on a cloud. And we recognize that Parquet is the most important data structure once you go scale out to larger data. Then CSV won't cut it anymore. Even if it's still the most ubiquitous data format out there, it won't. So we've been working hard on that. We've been working hard on I/O plugins, I/O improvements, non-equi joins. Does everybody know what this is, a non-equi join? No, okay. I'm going to explain it a little bit later. And we have a new plotting backend. Also come back to that. Polar's Cloud and new streaming engine are something we work on, but it's not released yet. So we're working on that on our backlog, and I put it on the right because you will be able to use that later. So it doesn't feed back into the main release yet. So Parquet performance, we recognize that our Polar has its own Parquet reader, which is really important if you want to do fast. If you're a query engine, you want to push the filters down into the reader and make sure you only load the data you need. And we want to be able to run every filter you've written in the Polar's expressions effectively in our Parquet reader. So we need to own the reader as well. But this is also a very huge technical depth you take, right? So we recognize that we were not as fast as we wanted, so we've put a lot of effort in this. And here you see the results of Polar's the main branch compared to Polar's version 20.16, 0.20.16, which is a few months old now. And you can really see that we improved on almost all dataset sizes with different queries, and some are super impressive, right? 5 times faster. It's much more correct now. We use SIMD to decode a lot of encodings. SIMD means that you use special CPU instructions so you can move more data through it, which needs a special kind of programming. Let's put it like that. That's sort of in a nutshell what SIMD is. And we have a pre-filtering optimization. That means that in a Parquet file, you have different chunks of data, and if you load a chunk of data, you then need to filter the rows you selected. You can also get a data dependency in there. So what you can do is first create a mask of the rows you want to filter on the predicate. So the predicate is the filter you write. And when you have that mask, you can use that mask to do the decoding later. And this can save a lot of time because you don't have to, for instance, if you have a very long strings in that Parquet file, you first need to allocate all those strings and then you filter out a lot of those strings again. So if you don't have to load them, it can save a lot of memory allocation. Another feature is non-equi joins. We have a new algorithm, which is a parallel IE join, which is one of the I believe it's the fastest non-equi-join algorithm out there, to my knowledge. I know that all database vendors are trying to implement this one, or are implementing this one. A non-equi-join is where you have a table and you want to join it with another table, and you want to join it on predicates that are not equal. So normally, if you do an inner join, the keys of the left table need to be equal to the keys on the right table. That's an equi-join. Then it needs to be equal. If it's non-equal, you say the key of the left table needs to be bigger than the key of the right table. These kind of joins need different algorithms, and they're a lot harder to do performant. So I'm super happy we've now implemented this. Before you had to do a cross-join plus a filter, which explodes your data, and then, so this is 100 times faster than what we did before. And you can see if you write this query, you will get this logical plan, and you see that it detected an IE join algorithm. Another thing we have is the plugin system. We already have to. Who was at Marco's talk before here? Yeah, he showed what the plugins were. So plugins give you a lot of nice things. It gives you native performance, native integrations, your own expressions that integrate with the Polars expressions, parallelism without interference of the Python GIL, and we wanted to extend this to I/O plugins because we recognize that there are a lot of I/O formats we don't want to support, sadly. There are a lot of file systems we cannot support because it would increase our binary size of the binary we have to ship. So yeah, we supported that. We now added that. It gives you a lot of the same performance improvements. Because of the time, I don't have much time left. I'm going to skip a little bit, but know that this exists. Another thing is that we have a new plotting backend. I always said that Polars wouldn't do plotting. I thought it wasn't important, but people convinced me otherwise. So here it is, and I think we have it now in a way that's good, because I think Polars should not own the logic of the plotting. I think there should be a good integration with a backend, and there should be a way to move forward if you see that its backend isn't doing plotting as nicely as we want anymore. And I think we have this now with Altair, thanks to Narwhals, which is a library that allows you to write. It's for library maintenance. It allows you to write a subset of the Polars API, and then it can translate that to Pandas, to Polars, to different backends, without requiring those backends to be installed. So with this, we have we can plot data without needing to convert to Pandas, which was required for a lot of other plotting backends. The world is changing. Finally, more and more backends, or more and more libraries are also now allowing Polars as a native integration. And also, finally, a lot of libraries now allow Polars without converting to Pandas under the hood, because, yeah, that's wasteful. And we made a lot of I/O improvements. There's the list here goes on and on. So who's familiar with the FF spec, file system spec, FS spec? Yeah, it's a library that you can use, and you can open a data set somewhere on the internet, and it will download for you, and it will just work as if you pass it to Python Open. And actually, this is what we are building under the hood as well. In Polars, we want you to be able to pass a query, some data set, and we will download it and cache it under the hood and make sure that this cache stays alive for maybe an hour, maybe 5 hours, depending on what the time to live is. But it's wasteful to first download a Parquet file, and then the next query you access it again, and we need to download it again. So we now cache the CSV and the NDJSON files. We have native Hugging Face support. And here you see some benchmarks on this. What you will see is that the naive thing to do when you download a file is just download it, right? And if you just download it, it will be very fast. So that's what Dask and DuckDB, or Dask and Pandas do. They are really fast in downloading, 13 seconds. Polar's 12 seconds, DuckDB takes 2 minutes. Why is DuckDB slow here? Because DuckDB downloads in a streaming manner. DuckDB is a streaming engine, and every time it needs a chunk, it will request that chunk to be downloaded. But this, if you do this sequentially, you will be blocked. So this, I think that's what's happening here. But if you add a limit to this query, so if you download the file and you say, only show me the head and then collect, you will see that DuckDB and Polars are fast because they don't download the whole file. They only download what they need. But Dusk and Pandas will first download the whole file and then give you the head. And you can see that Polars does good in both directions. It's fast in downloading the whole file, and it's fast in only downloading what it needs. That's because of the async I/O part we've written in between. And we've worked a lot on correctness, the correctness of IR. And this is not so sexy, but this will eventually get you a lot of result, because at the moment, we still raise a lot errors. If you write a wrong query, we can sometimes just find out when we're executing the query, which sometimes is the only place where we can find out, but a lot of times we could have seen this statically before getting the data, which means we can give you results early. We can say, hey, this data type doesn't combine with this data type. You've got a bug in your query, which means faster interaction times, right? If you don't have to wait until the query is 20 minutes in, you can keep on interactively programming. But it also gives us a lot more information in our time system. And with that information, our optimizer can improve a lot. And with that information, we also can better implement our new streaming engine. Our new streaming engine is much more low level than our in-memory engine is. So you can combine it, you can compare it with, if you're writing Python, there's still a lot of information. But once the CPU is executing assembly, it doesn't know anymore that this was a Python for loop, and it cannot give you the error information that this was line 95 in this Python file, right? That information is lost. So to give you proper errors, to give you proper information, we need to catch this on a higher level. And the final thing I want to show is that we're working very hard on a new streaming engine. So Polars is super fast on in-memory data, but if your data doesn't fit into memory, you're out of luck, and we're swapping, which is wasteful, right? It just doesn't work. We experimented with a streaming engine, which worked okay-ish until the data model of Polars didn't fit that streaming engine, because the Polars data model is different than the data model of a typical relational SQL engine. And a lot of literature is mapped to this relational SQL model. So we had to figure this out ourselves, and we're learning about this a lot. And we now are building a streaming engine that maps to the Polars API and to the semantics of Polars. And we're really happy about this. We're learning a lot about those API. With that, our optimizer is getting better, our IR is getting better, but also our execution will get much more efficient in the new streaming engine. But it's actually very low level. So we're building a custom async runtime that will actually does this parallelism. The status at this point is that a lot of plumbing is finished. And it sounds really easy, plumbing, but this is, I need 1 or 2 talks to fully explain what we're building. And you will get this in one, I hope in a half a year, I promise. I have 1 minute left, so the demo I'm not gonna make. So in this 1 minute, I'm gonna take a breather and go to the questions. Thank you.
Right, lovely, Ritchie. Thank you so much for giving us all of those updates. You've been working very hard on everything. Mm-hmm. We have 5 minutes for questions. Are there any questions for Ritchie? Yeah.
Hi. First, thank you for the library. I've been using it for a while, and I'm really happy with it.
Cool.
But But I did want to ask you something, because in Python it has become a problem, the amount of dependencies that some of the open source packages seems to be getting at. If you see Panda's amount of dependencies, they seem to be quite big. And in Polars, they are smaller than the case of Pandas, but with the rise of open source supply chain attacks, I was wondering, what are the steps that Polars is doing to be able to scan those dependencies that you have to give some more resilience
Right.
users?
So the question is what we do to combat supply chain attacks.
Yeah, or to just scan for your own vulnerabilities or
We trust,
dependencies.
to be honest, we trust on open source here. We don't add much new dependencies because we don't want our binaries to increase. If you install Polars, you will have no required dependencies. Polars is just one binary. So on the Python side, there are almost no extra dependencies. On the Rust side, of course, there are dependencies because we have dependencies. And yeah, we trust on open source to find them. We have the notification. If there is I don't know what the bot is called, but there's a GitHub bot that will, the Panda bot? Yeah, we have the Panda bot. It will inform us when there is a known bug, and we act upon that, of course.
Other questions? Yes.
Thanks for the talk. You mentioned that now there's Norvals and then nice compatibility with the API, sort of with the DSL, with multiple engines, and you can go back and forth. How is Polars doing with SQL? So if I really want to write SQL but want to use Polars engine because it's super fast, do I have option?
Yes, we have a SQL front end that maps to the Polars DSL. It can do pretty much. It can do quite a lot. But it will not do full SQL. So recursive SQL is stuff that we're not going to do. We're working on it. It's getting better. If it works for you, great. It's actually quite powerful with regard that you can combine lazy frames with SQL and so you can combine them. So it allows for some meta programming that's pretty cool. But if you're expecting to write CTEs, a lot of them with 700 lines, I don't think we support that kind of SQL, to be honest.
Oh, thanks.
Yeah.
Perfect. Thank you for a great presentation. I'm curious as to what convinced you to support the visualization backend in Polars. You said you're not convinced at first, but your colleagues convinced you.
Yeah.
And especially in the context of you saying that other database packages and libraries will support Polars in the future, moving forward. Like, what convinced you, basically? Because I'm not convinced myself yet, so I'm hoping, like...
Well, the eager API, for instance, exists because we want to meet users in the interactive workflow. And in the interactive workflow, I got convinced that being able to make a nice plot will be very useful to users. What for me was important is that plotting shouldn't hold us back. So it should only be on the DataFrame, and it should be in its own isolated environment. And what we actually did, because of this, it's marked experimental or unstable, so we're allowed to break the backend. So I think plotting is more of a thing you do in a notebook and is less of a thing you will build your need backwards compatibility on. So the fact that we added unstable features in Polars that we could do plotting in a way that's really isolated. The amount of plotting code is super small, and we just dispatch everything to Altair. So that also makes sure that we can focus on the things we're good at, which is building the engine, building the optimizer, building the API. That's what we want to focus on. And luckily, we were able to meet the users in the Pandas use case, where you say, hey, I want to do interactive workflows with nice plotting features. That doesn't hurt us. That's the answer.
All right, we have time for one more question.
Yeah, does it work?
Yeah.
You mentioned that you're developing your own async runtime, and I assume that's for Rust then. And why is there the need to develop a new runtime? And why did the existing runtimes do not work for you?
So typically, async runtimes are used for async I/O. And we wanted to use the power of Rust. This will be a bit technical. We want to use if you write async Rust, Rust will build a state machine for you, the Rust compiler will build this state machine for you, which can lead to very ergonomic, complex state machine async workflows. So we wanted to do work-stealing parallelism, but then, so work-stealing parallelism splits data into morsels, and then those morsels need to be handled in parallel, and we wanted to have a state machine to handle which morsel needed to go where, and we wanted to use the power of Rust together with this model. So we're using Rust. Can we use the Rust compiler in its strength for something that it's never meant for? So the async keyword was never meant for compute-bound work. We're going to use it for compute-bound work. So it needed a special custom runtime, specially tailored to this morsel-driven parallelism. And then for the I/O-bound asyncness, we still use Tokyo. So we will have multiple runtimes working together, and that actually works with Rust. Yeah, it's something bespoke only for this model, and it's also not used for anything else.
Yeah, clear, thanks.
Yeah.
All right, then thank you for all of your questions, and especially thanks for Ritchie. Give him one more round of applause, please.
Cheers.
All right, we'll continue in 10 minutes with the next talk.